Hello, everybody, and welcome for DV Club today on the 23rd of April. Our topic today is formal verification, and we have 4 speakers on that topic. Before we start, quick thank you to our sponsors, Agnesis, Cadence, Brecker, Synopsys, and for Testsolve for hosting the event. Okay. Today we have 136 attendees, all remote. We're not doing physical DV Club meetings at the moment. And that represents 77 different companies across 25 different countries. As I say, we have 4 speakers today. Our first speaker is from Marvell Technology, Braj Mohan Sharma. And then we have 2 speakers from Testsolve, Ishwa and Savita. Our third speaker is Alexandra from Cadence, and our final speaker is Nina from Agnesis. Okay. And as I said, a big thank you to our sponsors. So without further ado, I will stop sharing and I will pass over to our first speaker and then make the introduction. Thank you.
Rich, can you please share your screen? Yes, thank you. We can see your screen.
Okay. So our first speaker today is Braj Mohan Sharma from Marvell Technology. He is a senior staff verification engineer there. He has over a decade of experience in the field of design verification, with 10 years dedicated to formal verification. He specializes in IP verification, use constraint, random, and formal verification, and worked with leading companies including LSI, Broadcom, Intel, Imagination, and he is currently with Marvell based in India. And the topic for his talk is advanced formal verification and robust regression strategies for highly parameterized designs. Over to you, Raj. Thank you.
Great. Thanks, Mike. Thanks for the quick introduction. So let me start my presentation. Okay, just a second. Okay. So as today, my presentation.
Sorry to interrupt, Bridge. Your screen is not visible actually.
Oh, really? Okay, let me just reshare again.
Yeah, I can see your slides. Correct. Thank you. You can continue.
Yeah. So today my presentation topic is advanced formal verification and robust regression strategy for highly parameterized design. So here we will explore strategies to verify highly parameterized design using formal verification, and we'll see some of the challenges which are related to these type of design. So our presentation agenda has 4 main sections. So first we'll talk about introduction, then we'll see the problem statement, and finally we'll walk over to the solution and results. So introduction. So we'll begin with the introduction of parameterized design here. So this type of design is specifically used for IP development, okay, because these parameterized designs support diverse design variants for specific goal, okay, and which can be used for different configuration, okay, and because it promotes the scalability and expands the design space beyond traditional methods. So here's an example, and this will be our case study as well for this presentation. And this is an example of a parameterized memory controlled IP and its usage with different instance. So as you can see, the different instance with different parameters, each instance will be a different design altogether. Okay. So for an IP with hundreds of parameters like a CPU event controller, there can be millions of design variants. So when it comes to verification, it's very crucial to verify all logic and design variants for a complete sign-off. And for that, I'm using a formal verification here. So I will not go very deep into formal verification as a technique, but we'll just touch upon what is a formal verification. So formal verification, it exhaustively basically verify. It uses mathematical proofs to validate correctness of the design. And like how it does basically, it verify design functionality exhaustively from all the state space, covering all the state space. And with that, like it identify all bugs, including those in the corner cases, and which is difficult to find by traditional approach. So with that, we can say like it provides a higher confidence in design correctness compared to the traditional methods, which is another simulation-based method. So this is about the introductions. Let's jump to the problem statements. So here our problem statement is associated with the characteristics of the design. So what is my design here? It's a highly parameterized design. And what is the main characteristics of the design? Because it supports multiple design variants. So we have seen the previous example where like event controller, it can have millions of design variants. But for this presentation, I'm using a memory control block, which is the internal block in one of our SoC. So it has 16 different parameters. So which means like it can have a total design variant how 2 power 16, which is 64,000 design variant it can have. Okay. But for the particular SoC for which we have developed this IP, we found 80 unique and valid combination, which itself is a huge number because verifying 18 different design variants is not a simple task. And so with this, there are two main challenges with the formal verification, since that's the technique we are using here. So one of the challenges, we have is creation of parameterized formal test bench. And the second challenge, which is the main challenge, that is verification of all the design variants. So we'll walk over both the challenges and see like how we are achieving our goal with the techniques discussed in this presentation. Now let's shift our focus to the solution, and this solution is for challenge 1. So here, so we'll address our first challenge, which involves creating a parameterized test bench. So here we will perform a parameterized formal modeling because that's the main part for developing a test bench for the formal modeling. So as demonstrated in the code snip here, and I'm doing this for a debug write tracker, for which I'm tracking the debug write which is happening in the memory controller. So as you can see, just like a design which is parameterized, so I'm modeling my formal tracker in the same fashion. So I'm using the generate block to which is inside of my auxiliary code that basically repeat the same code for multiple times based on the number of times. And similarly for creating a logics, okay, write data sample or write ongoings, I'm using the actual parameter which are part of the test bench. So here, like you can see, there's different parameters: secure memories, the write disables, the single port memories. All these parameters I'm using while creating the auxiliary code. Now, while writing a formal properties, we should follow the same. So here also I'm using the parameters inside my properties, and along with the parameters, I'm basically using parameter to enable and disable the properties based on the dates. So that's how we basically model our test bench for parameterized design. Now, our next solution, which is for the challenge 2. So before like jumping to the solution, let's recap our main challenge here, which is related to verification of this IP. So our verification goal, our verification goal is not just to find the bugs to achieve a bug-free design, but also detect a bug early in the design phase. So you don't want to find a bug towards the end, let's say during the tape out. So that's our main goals. And to achieve that goal, actually, we do a different level of verification. We do the block level simulation. Okay. So the main challenge here is like for such kind of IPs, you need to have a different database with a multiple parameter combinations. okay, in order to target such kind of IP. Similarly, when modeling the formal test bench for the same, we need to do the same thing here as well. Okay, if you are going with the traditional methods. So with that, we can say in the block level, verifying all design variant possesses a challenge. And when it comes to the full chip simulation, then it's a total different equations, because in the full chip simulation, in the full chip, you will have all the variants which are used inside the SoC. So covering all variants is very easy, but the catch is it's not exhaustive. You don't cover all the features which are related to those variants. So we can say like we don't verify, although we cover all variants, but we don't exhaustively verify our IP with a full chip simulation. Now let's shift to the solution here. So here I'm proposing parametric formal regressions, a technique to target such kind of IP, where running a formal regression for all supported parameters. So here is a flow as part of this strategy. So here with the different parameters, there can be large param space shown here. So first step would be to create a reduced param space, which is nothing but creation of list of valid parameter combination. So we'll see those in the next slides. And this we will do until we reach our target. Now, our next step would be run a regression. So what we will do first, we will analyze our design. That means elaborate or compile our design with each param configuration from that reduced param space, and finally run the regression and analyze our result. So this is a flow for the parametric regression. So now let's dive into the parametric regressions. So previous slides, we have seen the flow. Now we'll see the implementation part. So while setting up a formal verification, so during elaboration, or we can say design compilation, we can pass the parameter with their values. So this lets us create a different design variants without changing the default parameter, which is inside our design. Then we have this, we'll bind the test bench and duty together. And with that, we can bind those parameters to TB as well. So if we configure the parameter during the elaboration, then the same parameter will be passed to the TB as well. The next step is to create a reduced param space. Okay, so where we will list down all the parameter combinations. So this is the for that I'm using an Excel sheet where you will have all the parameters and with there all the combinations which are basically valid for that particular SoC. And to do that, I have implemented a unified formal verification flow to automate this. So as part of this flow, it will take a list of parameter from that list. One by one, it will take the parameter row from that list. And it will elaborate the design using those param values. And it will prove the assertion and save the result. And it will do the same until all the rows are done. That's the regressions. And here is an example like how it happens in the tool. So we have a Synopsys PC formal and the Jasper board, both supports are there. So, and this is a command like how both the tool elaborates the design top using the parameters with name and with their value. With that, you can run the regression. So now let's touch upon the unified formal verification flow I was talking earlier, where this strategy has been implemented. So this flow helps set up formal test bench in unified manner, as shown in the diagram. So for every flow, we require a file list with the test bench and DOT files. So that you have to pass to the flow. And additionally, there is a formal configuration file which we have created, which contains a set of predefined attributes that assist in configuring the test bench. And some of the attributes are listed here. So the top, so where you need to specify your design top. And then you need to specify the clock and reset associated with your design. The param file. So this is the file which you have to specify where all the parameter combinations are listed down. And then the tool, because it can support multiple tools, and the Jasper Gold VCS, there's a plan to support the Siemens as well. And then there's additional parameter, which is there, the param row, that's for a debugging purpose, to debug the specific variants. Let's say you don't want to run a regression. So out of, let's say, hundreds of parameter, one specific parameter combination you are interested in. So if you specify that the row number here and run the tool in the debug mode, then it will invoke the tool for that particular combination. That's for easy for debugging purpose. And then the mode, which basically tells whether you want to run the regression mode or the debug mode. So with that, actually, those unified way formal verification flow, what we say, we avoid scripting. So when you avoid scripting, that means it becomes unified, because scripting is user specific. User can write script in their own way. So once you avoid or minimize the scripting work and have some unified way of configuring your test bench, that becomes a flow which can be similar across all the project or all the basically formal verification test benches. Right. And additionally, this flow provides periodic regression support as well, which is very important, because that way, like, you can track the changes happening in the RTL design future. So you can basically select the period like weekly or once or 2 week, you can run the regression so that whenever there's a change happening in the design, you can catch easily. Okay. Otherwise, the normal formal verification is like you prove the design and then you forget. Okay, then once you get the issue in the simulation, then you remember, okay, yeah, we forgot to run the formal run again for that design because there's some change. That way, we can basically track your changes happening in the RTL in the future. Right. Now let's discuss the result here. So we have some very fantastic results to show. So I have formally verified the memory control block for 80 different design variants. And I have divided the verification effort into 3 major milestones. So in this graph, we will see a bug report summary for each milestone. So in the first milestone, during the initial setup with a test bench using a default parameter. So it's just initial test bench setup. So I discovered 10 bugs because initially when the design is fresh, test bench is fresh, okay, it's easy to find a bug because normally that's what happens once you design the IP counts up. So moving on to the second milestone, where I used a parameterized test bench, okay, and manually proved 5 variants. I picked up 5 variants, and with those 5 variants, I ran the tool. I identified 7 more bugs. Okay. So, and in parallel, I was working on the flow, the parametric regression flow. So once the regression flow was fully operational, I ran the regression. Okay, and I uncovered an additional 6 bugs. And these findings were significant, especially since they were corner case bugs related to different variants. And more importantly, I discovered these bugs very early in the design space. Earlier, whatever used to happen is we used to find this bug when you are running a full chip simulations, which is towards end of the code complete. And during that time, like when we are randomly selecting some of the IPs for sending the traffic, and we find a bug. And then like fixing those bugs were costly during that time because a lot of PD work happens already. Okay, but here we achieved that much earlier. So now let's look at the time spent during each milestone in this particular results. So in the first and second milestone, I invested 12 and 8 days respectively. However, during the parameter regression, within just a couple of days, where total regression runtime was 15 hours, I was able to uncover 6 additional bugs, which you have seen earlier. So this demonstrates a significant return on investment with this approach. And after that, it's just a matter of running regressions. Whenever there's a changes happening in the design, it's just a matter of running regressions. So that's the benefit we are getting with this particular approach. Okay, so now I'm about to conclude my presentation here and with the 3 key takeaways. So first one, which is the main one, that to prove parameterized design exhaustively, because with this approach, we were able to achieve the complete exhaustive verification of that IP. So second one, basically, it's about the flow, because this flow provides a debug mode to run a selected variants for debug purpose. Because I used to get a lot of requests from the designer because once they are fixing some of the issue and they are only interested in those particular variants, can you please run quickly run the formal run to identify if there are any bugs for that particular variants. Okay, so that's very important. Okay, the debugging purpose. And the third one is, of course, the enabling the automatic periodic regression to track the design changes. So these are the three key takeaways from this approach. So now here is the future work that is currently in progress. So I'm working on a Python-based automation script to generate a parameter list automatically, because, well, this example is very easy where we have 80 variants, although the creating a list with the 80 different variants was again challenging. But once you have, as I took the example of the CPU event where millions of events are possible, although not all basically combination are valid, but still if let's say the combination goes beyond 100, actually it's impossible to basically list down all those things in a sheet of paper, in a sheet. So that's why I'm working on this automatic generation of parameter list, and it's a Python-based script which basically will constrain the parameter, and based on those constraints, it will generate a list of all the combinations under those constraints. And then I'm working on the constraint optimization as well, because what happens is when you apply some constraints, and with that you get the list. But with that list, you are not able to cover all the logics, which is part of your design. So then the constraint optimizations will come into picture, where how you need to optimize some. So automatically you can do that. Once you pass your result to the Python, it will automatically optimize your constraints and generate a fresh reduced param state space, which you have seen earlier in a parametric flow. The next part, I'm working on the creation of configuration coverage. Okay, because once you have a configuration-based list, okay, it's very important to have a coverage as well. Okay, because the coverage, you will know that what are the configuration you are covering with your flow. Okay, and let's say your script is not covering some of the parameter combinations with the automatic generations, you can quickly catch with your configuration coverage. So it's very important to have those kind of coverage. And then finally, the parallel regression flow, because this was again one more improvement, because we were not able to do that because of the license constraints. Okay, but I'm working on in this flow where you can parallelly run multiple test cases in the regression to reduce the total regression time. Right. So with this, I'm done with my presentations, and I'm open for Q&A. Thank you.
Thank you very much, Raj. There's a few questions. We have some time as well left over, so you finished a little bit early. So the first question is, has this been used both on IP and SoC, or just IP verification?
It's for IP. So usually, like the formal verification FPV, okay, the formal property verification is on the IP. Okay, we don't do those on the SoC, because in the SoC the design state space is very huge. Okay. Still, okay, although there are techniques, yes, but here we are talking on IP only.
Okay. And one more question from us, from the audience as well, is do you always look at all combinations of parameters, or are you able to scale that back a bit and look at different combinations? So
as we have in my flow, let me just go back to my flow. That way, like I can explain you. Yeah. So here, as you can see, like since param space could be very big here, like you can see select param space. So we don't do complete param space because it's not very useful to run regression on complete state space. So with that complete space, you identify a reduced param state space which is valid for your SoC. So in this particular example, we have a 16 parameters. So our complete state space is 64,000. But I'm not doing that. I'm doing for 80 because that's what we identify while analyzing the SoC. So that I did manually, but as I said in the last slides, I'm working on automatic flow where we can do based on the constraints. Yeah.
Okay, and the last question that someone's given is just, so how much time and effort do you think this flow has saved you? Maybe per project or across all projects?
Right. Yeah. So that's a really good question. Okay. The time wise, as I said, like usually such kind of things happens in towards the code complete, because when you have such kind of IP which is used across multiple IPs. So this particular IP used in the memories, and in our project we had around thousands plus memories. To cover all those memories, we don't cover these memories during the initial phase. We cover these memories when our full chip simulation is ready. And so towards the CC, we basically do that. And but we were able to achieve this during the initial phase of development. So we in terms of time, so we were able to do this 3 months prior to how we supposed to do before. So 3 months prior, we were able to achieve the complete sign of that particular IPs. And about the time saved, as I said in the formal parametric regression, in couple of days we were able to cover 80 IPs. If we could do this manually, it could take a week's time to do that in formal as well.
Okay, very helpful. Okay, thank you very much. I think there's a round of applause for you as well online. So thank you very much.